Every time a user clicks on your website or mobile app, they're telling you about their preferences and what they're looking for. But how do you harvest that information to improve the user experience, build novel features, or drive additional revenue? And how do you build a system that does this in real time, at scale, and on a budget? See, real-time data processing is often complex and costly, requiring large teams, months of development, and expensive technology. That's why we at DataSQRL partnered up with our friends at Redpanda to show you how to build a real-time clickstream recommendation engine that uses generative AI for personalized content recommendations. And we are going to build that real-time recommendation engine with open source technologies in just 45 lines of code and an hour of your time. This diagram shows the architecture of the recommendation engine we're going to build. When a user clicks on a web page or mobile app, we're recording the interaction in Redpanda. Redpanda is a streaming platform that can handle large volumes of data. You can think of it as a persistent queue with a playback feature. From Redpanda, we're going to ingest the data into Apache Flink, which is an open source stream processing engine that's scalable and fault tolerant. That's where we will be analyzing the data to compute personalized recommendations. We're going to use a large language model to compute vector embeddings that are going to help us to determine the specific semantic context that a user's in, so we can serve content that is related to what the user has previously looked at. Those recommendations are then stored in Postgres, the Postgres database, from where they are served to the user through a GraphQL API on request. Now you may be thinking, whoa, that looks like a lot of work. Not only do I have to implement 4 different components, I have to also stitch those components together, make sure the data moves smoothly between them, map all the schemas, take care of the timestamps and the watermarking, and finally fine-tune the whole thing and get it all up and running. And you'd be right. That would be months of tedious work to get that all working. Luckily, we have a trick up our sleeves, and that trick is called DataSQRL. DataSQRL is a tool, a compiler that takes SQL and the API definition and compiles the entire data pipeline for us. That means we only have to write the logic of our recommendation engine and the way we want to expose the results, and DataSQRL takes care of the rest. Let me show you what that looks like. With DataSQRL, we implement the logic of our recommendation engine in a SQL variant that you can see on this screen. First, we're going to import our clickstream data and the content that the user is visiting. So this would be our web page content. For this demo, we extracted a subset of Wikipedia pages that contained the word real-time to have an example corpus of websites. Those are ingested from a Kafka topic that you define in DataSQRL as a dependency in the your data package that we're importing here. Next, we are defining the actual analytics for our recommendation engine. First, we are going to determine which websites are frequently co-visited, meaning when a user visits one web page and then navigates to a separate page on our site, we keep track of that transition. This is what this join does, where we do a self-join on the clickstream data. And in this case, we are limiting this to 10 minutes, meaning we're looking at pages that the user visited after a certain page within 10 minutes, because that means that those pages are likely related, and we use that for collaborative filtering, meaning we use that to then aggregate which websites are frequently co-visited. So we look at the frequency here by grouping on the URL and the recommendation, meaning the other site that's frequently visited, and then use the ones that are most frequently co-visited as recommendations to serve to our users. So that's a nice and easy way to build a real-time recommendation engine that looks at the paths that your user take through your website and use those to recommend likely related pages to users visiting your website. The other part of our recommendation uses vector embeddings in order to compute a semantic profile of our users. What does that mean? Well, first, we compute the embedding for each piece of content on our website. We use an embedding model that we download. It's a publicly available pre-trained embedding model that works on a large, was trained on a large corpus of documents, so it works pretty well across the board. We then deduplicate the content stream that we're ingesting, so we get the most recent version of every content on our website. And then what we're going to do is we're going to join each click that the user places on our website with the vector embedding of that website. So we get the vector embedding of the page that a user is currently on at the time that the user visited the website. And then we aggregate all of those vector embeddings by taking the centroid of those vectors. So in a way, it's sort of the mathematical expression of saying we're going to look at all the content that the user has visited. We're going to compute a semantic mapping of that content. So that's basically just a vector, meaning a number representation of what this content represents. And then we're taking the center of it. So we're basically averaging out all the content the user has visited to get an understanding of the kind of content that the user is interested in. And we store that in the user interest table. We then use the user interest table to retrieve similar content. So when a user visits our website, we look up the similar content table by user ID, and we use cosine similarity between the pages of our website and the user interest vector that we computed to determine how likely it is that a user might like a certain web page. And we retrieve the top 10 most similar. Cosine similarity is basically it's a fancy way of measuring how close two vectors are, and therefore a way for us to measure how close semantically related two pieces of content are. So that in a nutshell is all the transformations that we're doing. And as you can see, we can implement all of that in just 27 lines of SQL code. The other part of our implementation is the GraphQL API. This is how we expose the data to the user. As you can see, the endpoints, the query endpoints that we're exposing is a recommendation endpoint per URL. So we can look at other URLs that are related to it by user content paths. And then looking at similar content for a particular user ID, like we just described. These endpoints map to the tables that we defined in our squirrel script, and that's how the API gets then exposed. That's all we have to do in order to implement our content recommendation engine. The DataSQRL compiler takes care of the rest. When we invoke the compiler, we can see the results in the build directory, and specifically the output in the deployment directory, which includes all the various deployment assets that we need for our data pipeline. You can see how all these components fit together if you look at the generated Docker Compose file, which includes the database. This is the Postgres database using the pgvector extension that we need for our semantic similarity search. You can see Flink, the job manager and task manager. You can see Redpanda being started up for our streaming platform. And you can see the server engine, plus a couple of admin/bookkeeping jobs that we're running to submit our Flink job. So this is what stands up the entire data pipeline. You can run this locally to see how it works. In fact, this is what's running over here right now. I already started up. It takes about a minute or two for the whole data pipeline to stand up with all the components and having them all connect. You don't have to do anything. You just have to wait a little bit depending on how fast your computer is. So we have the pipeline standing up. We can actually look at Flink already running. So if you log into the Flink dashboard that we sort of automatically mapped to port 8081, you can see your job and you can see the various tasks in the job. And as you can see, there's not much happening right now. We haven't really ingested any data. This is our Clickstream source. So this is where it reads the Clickstream data from Redpanda. As you can see, there's nothing happening. So the next thing we need to do is feed it some data. Let's go back. We have a little Python script that we use for this that ingests the Clickstream data from a JSON file and then publishes it to Redpanda at 100 messages a second. And so when I run this, you can see that it'll start up and it start reading and start publishing those messages to the Redpanda topic. What's happening behind the scenes now is that this little Python script will connect to the Redpanda instance that's running and push the data into the Redpanda instance. So we're basically simulating about 100 clicks per second on our website that are being published to Redpanda. From there, the Flink job picks up the content. So as you can see now, we can see that we have already consumed about 2,200 of these clicks. Now this gets updated a little asynchronously, so you can see every 5 or so seconds, this will jump, this number will jump up. And then you can, if you zoom out, you can see how all this data is then being processed across the board. So now we should start seeing some data as it's being processed. So we're going to go against the GraphQL API and retrieve related web pages to this particular website that is one of the Wikipedia pages in our sample data. And we can see other pages with the frequencies updated. We can also look at similar content for a user. So we have a user ID. We used randomly generated UIDs and look up the similar content that is suggested for that user. You can see all of that works really, really fast. The GraphQL API is very fast. It works directly against Postgres. So you can pull out these recommendations in milliseconds since they were all already pre-computed in Flink. So it's really fast to pull them out of the Postgres database, and you can throw thousands of transactions per second at it. All the while, in the background, we keep pushing messages into the queue, and Flink keeps processing. So we're about 10,000 clicks in at this point. If you want to learn how to build a Clickstream content recommendation engine that works in real time at scale yourself, all of the sample data and all of the scripts we look at are open source and under this GitHub repository. So you can follow step by step along to see how all of this works. I also highly recommend that you read the linked blog post that contains a lot more detail, goes through the DataSQRL script in detail, explains how all these components fit together, and will provide you a lot more information on how this whole system works overall. I hope you enjoyed this little tutorial, and good luck building your own real-time Clickstream recommendation engine.